Section: Introduction. In this section, we will introduce concepts from continual learning as well as parameter-efficient fine-tuning, which are relevant to the rest of our paper. Continual learning means training machine learning models on a sequence of datasets, which must be processed one after the other. At each step, we want our model to perform well on all the datasets seen so far. Starting from scratch on each dataset is called joint training and is considered the best in terms of performance. Continual learning methods aim to achieve similar performance without the inefficiency of training from scratch every time. However, in our paper, we focus on a scenario where we can only use the most recent dataset to update a model because we don't have access to older datasets. There are different continual learning scenarios based on the relationship between datasets. In class incremental learning, CIL, each new dataset introduces classes that were not seen before. On the other hand, in domain incremental learning, DIL, the set of labels remains the same, but the data distribution can change. Section Summary. In this section, we introduce the concept of continual learning, which involves training machine learning models on a sequence of datasets to efficiently learn from new data without forgetting past knowledge. Continual learning methods aim to update models with new information while maintaining performance without the need to repeatedly train from scratch. We explore different scenarios in continual learning, such as class incremental learning where new classes are introduced, and domain incremental learning where the data distribution changes while the labels remain fixed. Section: Parameter-efficient fine-tuning for transformers. In this section, we will discuss parameter-efficient fine-tuning for transformers. We have seen that transformer architecture, especially in vision tasks, is known for its ability to learn strong feature representations. One specific architecture we will touch upon is the vision transformer, VIT, in app, sec, VIT. When it comes to fine-tuning transformers, it can be quite resource-intensive due to their size. To address this issue, parameter-efficient fine-tuning, PEFT, methods have been developed. These methods involve keeping most of the parameters of a base model fixed while only fine-tuning a small set of newly added parameters or a subset of the base model's parameters for a specific task. This approach enables the adaptation of large-scale models even on less powerful hardware. There are various PEFT methods available, with adapter being one of the initial ones. Adapter involves inserting a small feed-forward module after each multi-head attention layer. However, in this discussion, we will focus on two widely adopted methods in the community: prompt tuning and low-rank adaptation, LoRA. Prompt tuning has evolved from the practice of providing models with instructions added to the input. Instead of manually crafted text prompts, prompt tuning introduces trainable, soft, tokens in the input embedding space. These trainable parameters are initialized randomly and are added to each input before passing it to the model. This extension increases the sequence length and impacts the computational cost of running the model. Compared to full fine-tuning, prompt tuning significantly reduces the number of trainable parameters. On the other hand, low-rank adaptation, LoRA, limits the update of a weight matrix to a low-rank subspace. For a given linear layer with a fixed weight matrix, LoRA incorporates a low-rank increment, which helps in reducing the number of trainable parameters. In transformer models, LoRA is typically applied to certain weight matrices in multi-head attention layers to enhance efficiency. When comparing PEFT techniques, it has been observed that LoRA outperforms prompt tuning significantly for a single downstream dataset. However, it is essential to investigate whether this superiority holds in continual learning scenarios. To delve deeper into this comparison, we propose LoRA-based variations of two popular continual learning algorithms, S-prompts and learning to prompt, L2P. These adaptations aim to combine the advantages of LoRA with the existing algorithms, providing a more efficient and effective learning process. In summary, we have discussed the concepts of prompt tuning and low-rank adaptation, LoRA, in the context of parameter-efficient fine-tuning for transformers. These methods offer ways to fine-tune large-scale models efficiently for specific tasks, making them more accessible even on less powerful hardware. Section Summary. In this section, we provide an overview of parameter-efficient fine-tuning (PEFT) methods for transformers, focusing on prompt tuning and low-rank adaptation (LoRA). Prompt tuning involves adding trainable, soft tokens to input embeddings, reducing trainable parameters significantly compared to fine-tuning. On the other hand, LoRA restricts weight matrix updates to a low-rank subspace, particularly beneficial for multi-head attention layers in transformer models. These PEFT techniques offer efficient ways to adapt large-scale models for downstream tasks, with LoRA showing promising performance compared to prompt tuning in single downstream datasets. Section S-LoRA. In this section, we present a strategy called S-LoRA, which is a variation of the S-prompts method. Unlike S-prompts, S-LoRA does not require prompt tuning. Instead, we use LoRA-based experts for each new dataset. We allocate a new LoRA module and an output head for each dataset, while keeping the training and expert selection steps the same as in S-prompts. Both S-prompts and S-LoRA are specific examples of techniques based on PEFT methods, known as SPEFT, or SX. In S-prompts, we assign a set of prompt tokens for each dataset, whereas in learning to prompt, L2P, we have a fixed pool of prompts shared across datasets. These prompts are selected based on input through a retrieval step. Each prompt is associated with a key vector in the base model's embedding space, initialized randomly. The input is passed through the base model to compute a similarity score for each key vector. The prompts with the highest scores are selected, concatenated, and added to the input. For learning to LoRA, L2L, a pool of LoRA modules is allocated, and the same key-based retrieval mechanism is used to select a subset of them for a given input. Unlike L2P, where prompts are concatenated, in L2L, LoRA modules are combined additively using weight matrices. We conducted experiments comparing S-prompts and L2P with their LoRA-based variants and other baselines on domain incremental and class incremental benchmarks. The datasets used include Core 50, DomainNet, Split CIFAR 100, and Split Tiny ImageNet. We employed a VIT B16 model pre-trained on ImageNet 21K for fair comparison and focused on memory-free methods like EWC and LWF. Performance was evaluated using the micro-average of all datasets, considering the final predictor produced after observing all datasets. Hyperparameters were shared where possible, with the main difference being the prompt length for prompt-based methods and the rank for LoRA-based methods. Default choices were used for these hyperparameters, with variations explored during the investigation. Section Summary. In this section, we introduce a strategy called S-LoRA, which is a variant of S-prompts that utilizes LoRA-based experts instead of prompt tuning. S-LoRA involves allocating a new LoRA module and an output head for each new dataset, while maintaining the training and expert selection steps similar to S-prompts. Both S-prompts and S-LoRA are part of the SPEFT techniques, with S-LoRA specifically focusing on domain incremental and class incremental benchmarks like Core 50, DomainNet, Split CIFAR 100, and Split Tiny ImageNet. Section: Infrastructure and Compute Resources. In this section, we conducted our experiments on Amazon EC2 G5 instances with a single NVIDIA A10G Tensor Core GPU. It took us 72 GPU days to obtain our main results. We needed additional compute resources for ablation studies and development. Our main focus was on comparing prompt tuning variants with LoRA variants to show that prompt tuning is not inherently better for continual learning. We found that LoRA variants outperform prompt tuning variants across different benchmarks. For example, in the L2X family, L2L performs about 58% better than L2P on average, and on DomainNet, the improvement is around 59%. Similarly, in the SX family, S-LoRA outperforms S-prompts by about 60% on average and by 61% on Core 50. We also looked into the runtime efficiency of prompt-based methods. When comparing the L2X and SX families, we found no clear winner. Two factors that influence performance are the expert selection method and sharing the classification layer. We observed that expert selection is more crucial for LoRA-based methods like LoRA than for S-prompts, especially on class incremental problems. By introducing an improvement called SX++, which updates the feature extractor on data from the first task, we saw performance improvements of 112% on split CIFAR 100 and 113% on Tiny ImageNet. Additionally, sharing the classification layer led to higher average accuracy, especially when L2X showed better results. In terms of related work, fine-tuning for continual learning can lead to catastrophic forgetting. Various methods have been proposed to address this issue, such as adding regularization terms or continually adding new parameters. We focused on memory-free methods and discussed the impact of transformer models on continual learning. We also highlighted the significance of LoRA over prompt tuning and its potential to enhance state-of-the-art prompt-based algorithms.